Welcome. We now want to have a deeper look to the mechanics of the coding of architectural models. We will create a model like this, which is not exciting, but for didactical reasons it's quite okay. It will cover the topics I think important. It will show you how to turn the different aspects of coding towards very adequate towards architectural models. So the key idea is with coding that you don't have to do any redundant work. So any decision you're doing has a very specific place, and you don't have to put a decision at several locations. And then code is evolving it towards whatever you like. So this is the wireframe, this is the rendering, this is the logistics, this is calculations, or this is robotic control, whatever you like. It's always evolving toward that, but the nucleus or the code is very compact without redundancy if you're doing it well. Quite different to the drawing on CAD systems, where you have to do a lot of manual work, a lot of repetitions, and you have to change a lot if you change your decision. For example, recalibrate the grids or these kind of things, and you have to redraw, and you have a lot of manual work because it's redundant. And because I think architecture is not about the visual and it's not about geometry. It's about not Cartesian geometry in today's term. It's about talking about the building and making a poem as code. So now let's have a look how this works. So we distinguish between constituting the coordinates. So this is how to take space, put points in space. That's the first step. Then we go for topology, so we connect these points with edges and faces. These are the two next chapters. And then we make it real. So this is a kind of wireframe, the first things. This is just organizing space in the rational. We had the rational here. So in our last chapter, harmonics, we had the rational, which is the red points. So this is the first three chapters. Put everything in proportion in space. And then we go and in principle we get objects from a library, or we buy products on market and put them there. So therefore these objects, they have, I call it the dreams of the night, or they're product by rotating machines. They're produced by rotating machines overnight in the production hall. And then they are products. And these products are memories over time, so they're produced, and they are capsules of times or traces of times, or in contrast to architecture. Architecture is a red line. Blue is I think the design. So this is production, this is in the hall, and this is about time and optimization, simulation, producing, and so on, all these circular things. Take them, so in principle you buy them and put them to their place. So the columns, the beams, these nodes, the facade elements, and so on. This is, I would say, make the model real. So this is a rational setup, and this is to make it real. So therefore we looked at the harmonics here in this chapter. Good. Let's start. So as we had it with a starter, we simply have very few lines of numbers. We go in X. These are 5 X's, 1, 2, 3, 4, 5. Then we have in Y-axis we have 1 and a 4, so it's 1, and then length of 4 And in three in Z direction, we have 1, 2, 3, 4, 5. And we give that a certain proportion because our image here has a certain proportion, or a facade element. It's this. Then, as we did with the starter, we get these tuples. And these are our points. So this is how to constitute this space. And of course, we can pick each of this point and put it somewhere else, but this will be the next chapter in our series about complex geometry. So now we start with this super simple grid. First step of topology, we need to go abstract. So we say vertices. And this is just the number of points. So we have to assign a number to these things, an index. That's here. We simply say coordinates. We ask for the lengths, the amount of coordinates. These are 50. And then we make a range, so we put it to 50 elements. So that's the first thing. And now if we want to go for counting and for measuring, we render graphics with mesh regions in Mathematica. So, and here, these are the points in space. And then we can ask, for example, now this is assigned to R, and we can ask R, hello, mesh region, mesh cells of R, and then the 0 dimension, and then we get points from 1, points 50 points. So very simple. If we go for lines, this is the first dimension. We have none. We have faces, none, and we can have a lot, in principle, a lot of dimensions, no problem. Now we stop with 3 or 2, and that's it. We can go for the mesh coordinates. To give you an idea of how mesh coordinates of R. And this is a data structure which is optimized for measuring distances, countings, and so on. We will use it towards building information models and so on. So it's proper for that. It's not proper for good rendering and visuals. Good. So this is the first step. We can give other options, for example, if we set the options of mesh region, which is this renderer, and say we want to have the labels of dimension 0 as index. If we put that, then these are the numbers. We also can go for highlight mesh. We say point, so dimension 0, number 2, so this is this one here. We want to highlight this point, and then we go and see this is highlighted. So these are the principles to give an idea. Otherwise, you simply go here with all the detailed examples given with Mathematica. If you want to reset the labels, because it's disturbing if there are too many, simply say mesh region, mesh cells label, and reset it to nothing, and then this stuff here the renderer has other options, and now it's without. So very simple. This was with the vertices. Just how to manage it. Welcome. Now we want to go to the problems of large models. The interesting thing is that It looked a little weird and complicated with these principal mechanics, but I think that's it. You have to go, you need the kind of virtuosity with that. But with computing, you abstract from the size of your model, which is very interesting for architects. You don't hustle around with body jobs. So it's just an intellectual thing to build up your coded architectural model. And by that, you have a good position in the value chain and can earn money with it. So let's go to the large models and the specific problems there. Oh, come on. So now we want to go for a simplified version of the Roche Towers in Basel by Herzog de Meuron. So it's organized like this. In principle, it's a four-dimensional thing. You have these blocks, which is a three-dimensional cube, very simple in organizing. You stack multiple of them and build the tower. So this is interesting. Just as a reference, how to develop the things. This is my first company. I founded with my brother. He is operating that in Karlsruhe. And he was working, or is working on these towers there. And it's done like this. And you see all this like a chip design. He's focusing because the main problem in an architecture is the complexity of the building services, and most of the value is there, and most of the problems are there. It's not the construction, the facade, and so on, but most of the problems are here. So, which is not a principally different setup, but and problem, but this is how it looks like, and it looks very complex and complicated. But if you put it into the models, as we discussed in the last chapter, you see they're all the same. So this is the regularity. So these are the positions in space, and this corresponds to these red lines. These are the positions in space. This is the architectural model. So, and then they are filled with productions. And this is what we see here. So if you go here, these are the elements. The produced elements, and they are of the circular production, and they are designed and engineered and so on. And this is not the architectural job. The architectural job is to put these things into a spatial proportion and organize it. And then here you have these tables of the different trades, how to produce these modules, which are the tunes of the architectural partitions. So that's how digitales Bauen works. So just to give you an idea where it goes to. It's not too complicated in the architectural setup. So, and it's exactly what we explained in the last chapter on the mechanics of the coding of architectural models. So now we want to simplify that and look at the problem of scale. So this, in principle, is only combinatoric explosion and nothing else. So to put this four-dimensional thing, I made a function which puts x, y, and z and is able to staple it. So therefore, in this case, we have 5 of these blocks and put that together. It's running very slow on because it's so big in my demonstration on the cloud. Therefore, we switch to the desktop, and there's a good exercise how to see that. But you need a license for that. If you want to run it on cloud, simply delete several of these things, and you have a smaller skyscraper, and can run the whole thing with the code on the cloud. So, but now we want to go for with the desktop. This is Mathematica on the desktop. So take these things, copy this to the desktop. It needs no other library. So we could simply call it B1, and we have these modules. Now we go, simply check how this works. So we get a set of coordinates as we had it before, x, y, z coordinates, and we make a staple of it, multiple of them, copy, put them in a vertical line given by these numbers here, put them on top of each other. So here, this is a function to create the vertices. So this is always a pair. So here we are in geometry. So we have the x, y, and z coordinates. And here with the vertices is an index. So it's just a number, and then you are in the at night. So it's just the indexes. And you are on the, this is the objectivity, and this is subjectivity. So, and here we are with the vertices, and we have 1,700 points. So, to make the space. If you want to see that, for simplification, we just want to work on the graphs. We have we create a graph. So, and put these graphs with the vertex coordinates. So we have the vertices. We don't have any edge yet. We get the vertex coordinates to make it look like geometry, but it is a graph. No labels, vertex size, are just for convenience. And here is, this is our tower. Good. First step, this is the geometry. Copy that. You directly can make a copy to desktop of the whole file with this, but now I show you a more interactive version. So, topology. We need vertices we already have. Now we want to go for the edges. So, we used this kind of function on distance. We want to have all the edges. This is in very simple proportion here. It's just always 1 by 1 by 1. So we need all the connections, all the points with the distance to the neighboring point with a distance of exactly 1. So now we run in this problem here. Look, because they're 1,600 by 1,700, so we go in the millions of distances. And to calculate that, this takes years. Yeah? Well, not years, but time. And this is called combinatoric explosion. This works simple and very good with 100 and 500 and so on, and then with 2,000, you see it's half a minute or something. And this is not possible only because you get timeout in the cloud already with 2,000 nodes. And I will show you how to go around with this problem and how to deal with it, because this is very, this is a problem. It's only a structural problem you have with large models in comparison to small ones. It even takes more because of screen recording. Now it's there. So to check it, so it's a distance matrix, so it's a huge matrix with all the distances of all the vertices to each other. So it's about 2,000 by 2,000, so it's 4 million distances. And you can measure the size by binarizing, binarizing. We say compress at dm. Be careful with, because this is a lot. Now we simply want to, this is a binarizing, and then simply say string length, and then you get the bytes. So if you calculate that, again, this takes a lot to compress it. So it's about 10 megabytes of data. So it takes about a minute to calculate these distances. And this is not okay. Yeah. So let's go and look for how to, so we can work with it. And conceptually, this is a straightforward way, and I think it's correct. So if you are not, even you can wait for it for a minute or two, and then it's fine. This is not a principal problem. But I know I want to show you how to use the structure to the knowledge of the structure of the building. So there's a kind of implicit knowledge about that. We may have to make that explicit and use it to be fast, which is a conceptual problem. I don't want to have any kind of pre-assumptions in that. So therefore, this approach is conceptually, it's a proper one. Computationally, it's awful. So therefore, I show you how with an implicit, so with some kind of understanding of the data, which you always have to try to you have to forget about the meaning, and then everything keeps flexible. So, but now we imprint somehow the structure, a kind of pre-assumption of what is there. And now I want to show you that. So we have B1, go for one of these elements here, and just have a little more, less. So go here and say coordinates is this, just this, so it's not too many coordinates, and the vertices are the same. So now we have only 700. So this is for simplification, just to give you an idea how to deal with combinatoric explosion with some labor. This is really labor to do that. So what we have with the coordinates, we always know that in x, all the x should be in line, all the y's should be in line, and all the z's should be in line. And if we look at the coordinates, then we see that they are in a row. So, so there's, because of these tuples, they have a certain structure how to organize that, and we can implicitly use this structure to find our connections easily, because we don't have to search for each one of this. We just have to connect them to their neighbors, and then 114, 113, 115 is a connection, 124 would be a connection, and 214 should be a connection. So, and then we can use this structure to find that easily without this combinatoric explosion. So, for example, we take these coordinates and take a partition of these coordinates, and we had that here with 13. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So these 14 elements, and then the next starts. So, and this would be a line or a sequence of 13 lines. So we need a partition of 14, I think. So now we have this, and now we subdivided this list, and we have, this is 1, this is y, these are the 2, the next line, the next line, the next line. So that's fine. So take just the first for further development. So we see that, and now we need a line from this to here, from here to here, from here to here. Now we can switch from geometry to topology with vertices. These are our points. We can go to any of them. So these are other points, no problem. So, and now we want to make pairs, overlapping pairs. And this is another partition of this, 2 with an overlap of 1. So, and then we have these pairs. And they should be our line. To check that, we simply say these are our edges. And we have to integrate it in our graphic. We make a graphic of it. So to have it nicer, graphic 3D. This is for nice visualization. And we have the graphics complex off. And because this is on geometry, we need the coordinates. So, and then we need the line. We need the points. Point of our vertices here. So, and then we say red and line of our edges. You have to put that to all these indexes with their rendering and their style. Indexes, rendering, style corresponding to these coordinates. They should be the second element of the graphics complex. First is the coordinates and close it. So now we are with the graphics complex. We are fine. Graphics is just this, and that's it. Image size. What would 128 to make it not 2? Now we are here. So we have a certain line in the vertical in this case. Make it 22. So we have a certain line, so it works like this. Good. If we have this, we can go and ask the edges. This should not be just the second line. So we can imagine now how this works. So we can go for the number 12, others, and then it moving for all of these verticals. So now we want to do it for all of them. So simply take this out, make a asterisk, a pure function, and then map all the vectors on that. We can. This is just what we had. If we take that, then we have a list, not a single, a list of elements, not a single element, and therefore we have to make the map here, and then we have all the vertical lines. So for our graphics, we need a single list, otherwise we would have to map it here again. So therefore we are not interested in any more structures. So say flatten. So it's just the inverse to partition, make it 1, and then we have a flat list of elements with indexes. And if we display that, we have all the verticals. So we are happy with that. So you see it's super fast, yeah? So now go for the other. Now go, for example, for this one. Let's have a look again. If we go for partition, coordinates, so we are here. So then make that 1, 2, 3. So now we got this line and made a line of this. Now we want to make a line from here, here, here. So 1, 2, 3. To do that, we have to, this is called transpose. So this is now 14 elements by, so the dimensions of that, of this is 3 by 4, we can make it 6, for example, make it 6. So then we have 6 by 14 by 3. If we make that transpose, then we have 14 by 6 by 3. So that's what we have, or what we are interested in. And then what is in a horizontal line now turned the hierarchy of the list from the horizontal, at first the rows and then the columns. We first make now the columns and then the rows. This is what transpose makes. So, and now we have this line here. Well, as we want. So now it's not the Z, now it's the Y direction. Now we can go leave this. Now we have all of them here. Is it like that? No. Transpose. Is it correct? No, it's not correct. No, we just want to have, no, that's nonsense. You see, it's complicated. So we simply want to go here. We have to put it in 6. So now, by 14. Here we are. So now we have this, then we have the second, then we have the third. So now it's okay. Now we can go and make a transpose of this. Now we have 1, 2, 3, 6, 6. We have all these lines. Now they are fine. Now we're counting with the first number, so that's fine. Good. We have this. Go for vertices. Make the partitions again, and the flattening. And here we are. So go for edges and render it. Here we are, with all the lines in Y. Good. And now the last one. Okay, now we want to go for these, the last direction, it's 9. So this is the most complicated one. So go for the coordinates. We are here. We have to partition these coordinates. These coordinates by 14 by 9. Then we have these here, and now we want to go for these lines here. 1, 0, and then 2, 0. Here, 1, 1, 0, 1, 2, 0, 1, 3, 0, and so on. Therefore, we have to make a partition for each of that with 14. So therefore, partition of this by 14, and do it for all these partitions. And here we are now. We have these lines here, yes. Now we have our lines. And now we have to make transpose, we have to make 1, 1, 0, 1, 2, 0, 1, 3, 0, and therefore we need a transpose of these lists. And here we are. Now we see 1, 1, 2, 1, 9. So now we are counting about around the X. So that's, I think, it is. So now we can go switch to the vertices. This is here, and take all this and make our established scheme, partition, flatten, partition 1, and no, partition, so, and here we are. I think that's it. But because we had 2 of these rules, we have to flatten it by 2 to make so these are our edges, most probable. So if we check it, here we are. So now we can simply join the things. So make a list of this with, no, I keep it explicit, and make edges, combine the things, is copy, no, and simply join this one and this one and this one, and here we are with our edges, combined edges, and here we are with the graphics. So we've seen, now make a comparison with dm, just to show you what is the difference. dm, now with our coordinates, this is just a small box, and now we do a timing to see the difference. So this is the correct, conceptually correct way how to deal with these problems, because there's no structural implications in that. So time is 12 seconds. So it's double time with my computer because of screen recording. So if we do it like this, the same result, and we still don't have the selection and so on. So it's towards 14, 15 seconds. If we do this timing of this, we're 0.01. So it's 1,000 times faster. So therefore, in computing, you always, so computer scientists are super pragmatic people, and they are workers, and by that they somehow don't like to think about it conceptually, because they are always in this, and they always make assumptions, and they're implicit, and this is not, I think, what we need as architecture to keep these things vivid, adaptive, and so on, spectral. So, but you see, this is impressively fast, and this is how it works. So let's continue. No, this is with the home excursus, make an excursus here. So let's continue with our big model with the 1000s. And you see with 700 we have some 12 seconds, and it goes towards a minute if we have the 2000. So it's only 3 times more vertices, but it's 6 or 8 times more time. Good, it's still running. Here we are. And continue. Now, to look it up, these are all the distances sorted, which are, if you have all these vertices of your building, and if you connect and get the distances from each vertex to each other, and then if you sort these distances, delete the duplicates, then these are all the principal distances. And it's very very important that now, because in Mathematica we are working on symbolic numbers. So these are not computational numbers; they're symbolic numbers. Therefore, we can check on the exactness of irrational numbers. If you're with floats, you're always with with precision to a certain degree. So equality of numbers is very complicated to find. Here, you really can identify things with these small differences and so on. So therefore, in normal cases, if you want to ask, for example, for the edges in this 10 megabyte matrix, now we want to find what are the connections which are of size 1. So normally you have to work on it like that. You simply say, yeah, it's around 1, whatever it is exactly, it depends. In our case, we can go with the numbers as a symbol. So we simply ask the edges, we ask these 10 megabytes. We want to have a list. If there is a distance of 1, we want to have the position of this element in our matrix. So go here, and here it's another second, and then we have length, edges. We have some 4,500 edges, as we created here in a very short time. Good, these are our edges. We have edges, we can look them up. So these are our edges. They are all of length 1. So we can ask for example, now the diagonals, all the diagonals, then this should be square root of 2 in this case, and then we have all the diagonals. So beautiful. So this is how to go for the, which would not be possible with our calculation here. Huh? Very important. With the square root. Then we need another program to look for other distances. Here it's generic, but computationally heavy. So if we want to see that, let's go for a graph again. Now we go for a graph, have the vertices, we have the undirected edges, vertex coordinates to make it look like graphics, some options to make it to look nice, and here we are. This is our graph. And you see it's not too much. So there are now thousands of vertices, thousands of edges, and it's working. And the key problem is only rendering. It's not, for example, find shortest path and so on. Next level is the faces, and therefore we need the graph. Therefore we establish the graph. Now we want to have the faces. So we can ask with faces as we did it, with graph, get exactly all the four graphs, all of them, but then we would have all the faces at the inside. We don't want to have that. So therefore we have in a graph we have a nice, because it's about connectivity, we can ask for the vertex degree of the graph. So now we have the 2000 vertices, and we ask them, how many neighbors do you, how many connections do you have? So, and what we know is that the center, the vertices in the center, they have 6 connections, and on the facade they have 3, 4, 5. So therefore we ask for the vertices of the facade, we ask for the vertex degree, so this was this long list, and we look for the integer, for the position of the integers less than 6. So, because then they are at the facade. Flatten that again, and these are the positions, so the vertex numbers of the facade. Run by vertex degree, we can look it up how vertex degree works. So look at here, if you have a graph like this, or not a nice example. So here 1 is connected with 4, here 2 is connected with 3, and so on. So we can highlight graph of V facade. And here we see a screen recording is really, now we see all the vertices at the facade. Good. Therefore, now we make a subgraph of it. That's another command like highlight. We need a subgraph of this. So now it's the facade. All the vertices here. We see we have a problem with these edges because these have 6 points here. These two have 6 points. 6 is of degree 6, but they're still at the facade. The rest is okay. So therefore we have to find another function to create the vertices. It's this one. So we ask, is there another one with plus 011? Is there another vertex? If not, then keep it, even if it's of 6. So we go for vertex 2. Can try to analyze this function. Then they are part of it. So now it's closed. So these are all the vertices and edges we need for our facade. We could skip this, the bottom, if we like, but I think it's okay. So to show that, now we can go for the faces facade. Copy this. Now we go for the graph facade, which is this. This is a subgraph of graph. Go here. So with that, all the indexes are the same in this graph facade. He uses the same index as graph, so it stays in sync. And now we can find cycles, exactly 4, on this facade graph. And now we have all the 4 cycles here, facade graph. Now we go for a graph fix. because we can show it differently. So graphs, complex, the coordinates. Now we have red, the points, opacity, gray, the polygons of the facade. So we don't want to show the edges because it's with the polygons, lightning, neutral, and here we are. Nice graphics of these things. So that's, I think, is it here. Simple. And I talked a little around to make it clear where the problems are. They are not with the principle and the conceptual setup. They are more about computation time, memory, and so on. So you have to be a little pragmatic. Now it's super simple. Go for with counting. Set options here. Then we can go for a mesh. We can't do counting in graphics. We can, but it's not so comfortable. We do the same thing with the coordinates as we did with the graphics complex here. Coordinates, facade, we have the mesh region, and then we synchronize the cells so that they are the normals are all in the same. We put it towards element 1 or 2, it doesn't matter, or 200, doesn't matter. So then they're all in sync and all in the same phase and starting at the same point. So put that and get a nice region, mesh region. Come on. Here we are. And now you see the normals. And this is a very systematic way. So it's rough in implementation, but it's usable. So then we can, for example, highlight a certain element. We take this mesh and then we simply say of the line, we want to have line number 32. We want to highlight that. Then we see this is here. If we want to have the face number 32, it's here. That's a face. 320. Somewhere else. So we have all this. Then we can, for example, ask what are the different areas. This is so get for all the primitives R1, for example, how many of the faces are there. Then we go mesh primitives and they simply ask for length. How many are there? 922 faces. Then we ask what is the area, delete the duplicate and sort that, and this should be all the same, equals 1. Okay, that's the area. So then we can ask, it's a little too generic, it doesn't help. So go here. Then it says area 1 is element like this. With the irregular model then it will be interesting how many parts of which kind of size of area are there, and then you pack them in groups. So this is here, and group counts is here. Then you see area 1 is 922 times. So, and you can do any calculation of that, and that's it. Go further, but I think this is what I wanted to discuss with large models. It's not on the conception of how to do that. You see, it's the same vocabulary, the same tools we used in our prior chapter on the mechanics, but it's more on computational time, getting a little around with this, with computation time. But you buy a lot of disadvantages if you go into it what every computer scientist would recommend. And I would recommend simply wait for a minute to get these things done conceptually and keep your conceptual clarity of what you're doing. Good. This was a discussion for this module. Thanks for watching. Next will be on the problems we have if we go to an irregular geometrical model. Thanks and see you.